Hello, my name is Jana, and today I will be presenting my final project for computational photography, which is re-implementing a classic depth map multi-view stereo pipeline and evaluating it for dense 3D reconstruction. The goal is, given multiple calibrated images, to recover a dense surface. So my pipeline follows the multi-view stereo approach outlined in this paper, which first computes a depth map per input view, then fuses those depth maps into a single surface using truncated signed distance function, TSDF integration. I also built a conversion path from Colmap output so I can run the method end to end on my own photos, and I tested how capture setup affects those results. For per view depth estimation, I start by selecting a small set of neighboring views for each reference image, chosen to balance overlap with enough parallax to estimate depth. Then for each pixel in the reference image, I sample candidate depth along the viewing ray, but only within a 3D bounding volume. And this is important because it limits the depth range and it also makes the search more computationally feasible. So each candidate depth corresponds to a 3D point, which I then reproject into the neighboring views. I then compare small patches using normalized cross-correlation, and a candidate depth is only accepted if at least two neighbor views vote for it by exceeding a correlation threshold. And this multi-view consistency check helps reject incorrect matches that occur from occlusions, repeated textures, or accidental correlations. Then, once I have the depth maps, I fuse them using TSDF integration. Each depth map contributes signed distance updates to a voxel grid, and after integrating all views, I extract the zero level set using marching cubes to get a mesh. A key parameter here is voxel size. Larger voxels tend to give smoother and more stable reconstructions, but they lose fine detail. Meanwhile, smaller voxels can preserve finer texture, but they're much more sensitive to noise and incomplete depth coverage because fewer depth observations support each voxel. In the original paper, depth estimation is done with a more expensive search procedure, specifically a coarse-defined strategy that refines depth estimates with smaller steps after initial pass. I implemented that approach, and I also implemented a simplified version that uses a single pass depth search with a fixed depth step size along the ray. And the motivation for the simplified version was just the runtime. On the baseline Middlebury datasets, specifically Temple sparse ring and Dino sparse ring, each containing 6 views, the original version is extremely slow. So for example, the Dino sparse ring takes about 25 hours to run on the original version, but with the simplified pipeline, it takes under an hour. And the bottleneck here is the per pixel depth sampling combined with multi-view normalized cross correlation comparisons. The cost increases very quickly with the number of depth hypotheses evaluated. And qualitatively, the simplified version still preserves the scene structure, but it introduces more local noise and tends to lose fine detail compared to the faithful version. And that's kind of seen here, where this is the temple sparse ring. The top row is the original version, and the bottom row is the simplified version. And you can also see it here in the Dino sparse datasets. I also compared datasets that contain only 16 input views versus 47 input views. And with more viewpoints in the ring datasets, surface coverage improves and missing regions shrink, especially in occluded or weakly textured areas where sparse ring often produces holes or gaps. And this matches the intuition that dense MVS needs consistent multi-view support. If a surface point isn't viewed across multiple images, it tends to get filtered out or fused unreliably. Finally, I tested the pipeline on my own captured images using two setups. In the turntable capture, the camera is fixed and the object rotates. And this is easy to set up and it also keeps framing consistent. But the background stays static while only the object moves. And that means that feature matching and pose estimation can get dominated by the background structure unless the capture is carefully controlled with a clean backdrop. And in my results, that shows up as a less consistent per view depth estimates and more fragmented fused meshes. Meanwhile, in the camera moving capture, the object stays fixed while the camera moves around it, and this better matches the standard multi-view stereo assumption of a static scene observed from multiple viewpoints. And in my experiments, it produced cleaner fused meshes. However, it is still sensitive to practical issues like motion blur, lighting changes, and uneven viewpoint spacing, which can reduce the overlap and lower the multi-view confidence. And so here are some of the results using the turntable. As you can see, the depth estimates tend to be more saturated, but the confidence maps do look good and it does preserve detail. Um, Looking at some of the 3D outputs, you can see that um, they are very sparse and there are a lot of holes, especially in areas that are less textured, but you can clearly see the outline of the bow. And this is with the camera moving results. And so, although the fused meshes do look cleaner overall, there is still a loss of detail, and it can be quite sparse in regions, or it can have quite a few holes in regions that are less textured. But it does still look cleaner than the turntable results. Um, One interesting observation is that the original pipeline can produce very strong per-view depth, confidence, and correlation maps on real data. But it takes roughly an hour per reference view, and so for the full 54 view sequence, running all the depth maps and TSDF fusion becomes impractical, which directly motivates a simplified pipeline for real captures. So even though these depth maps and confidence maps do look sharper than using the turntable or than using the simplified method, um, it does take a very long time to run. And so I wasn't able to get a final 3D output using this method. To conclude, this re-implementation confirms that DepthMap MVS combined with TSDF Fusion is a strong baseline when you have accurate calibration and a good bounding volume. But in practice, it really depends heavily on efficiency constraints and on the quality of the captured images, especially for real-world image sets that don't have the controlled conditions of datasets like Middlebury. Thank you for listening.